Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. Thank you for coming. I'm very glad that Marjorie Skubic was willing to come over here and give a presentation today. Marjorie is coming from the University of Missouri, and where she's leading the Center of Elder Care and Rehabilitation Technology. I won't go over all of your background, but I just wanted to say that I'm amazed by the fact that she's actually trying to use technology for the benefit of people and successful in that. So, and this is what we're going to hear about today. So thank you very much.
Okay, thank you. Well, thank you for having me. And I hope that this is recording correctly. So I'm going to share with you some of the work that we're doing at the University of Missouri. And this is very collaborative work, includes a number of people across many different disciplines. And I'm going to give you a list at the end that shows you a lot of the different people involved. I've also included in here links to papers, and we have a website which I'm going to give you as well at the end. And so if you want to go back and look at some of the details, those are available. So here's an outline. I wasn't sure whether I'm going to actually be able to get to all of these things depending on how many questions we have. But I want to first give you a little bit of a motivation of how we got started in this. And then I'll step you through sort of a broad overview of some of the different aspects of the problem that we've been looking at. So to start with, we have a facility in Columbia, Missouri, where I live, called TigerPlace. It's named after the University of Missouri mascot. We're all kind of tiger crazy in Columbia, Missouri. And about 10 years ago, I had a nursing colleague, a nursing professor, wander across campus, gave a talk in the College of Engineering looking for collaborators. Now, at that time, they were interested in developing this new facility called TigerPlace. And they were working with an architect. They were exploring different possibilities. And Marilyn, this is Marilyn Rance, my nursing professor colleague, knew that she wanted technology to be part of this facility, but she didn't know what it should look like. And so she came looking for some new ideas. So TigerPlace ended up opening in 2004. It's actually a very interesting partnership between a private corporation. It was built and is operated by AmeriCare Incorporated, which is a Missouri company. But there's a partnership with the university. In particular, the nursing school went out and found AmeriCare as a partner. The nursing school operates a home health agency and employs the clinical staff at TigerPlace, which has some great advantages for us in terms of doing research. And it was really set up to become a bit of a living laboratory, if you will, as a result of that. So TigerPlace now has 54 apartments, and it really was designed for aging in place from the very beginning. In fact, it required 2 rounds of state legislation in the state of Missouri in order to allow TigerPlace to open in its current configuration and really be a true aging in place kind of facility. So there's 54 apartments. People can stay there through the end of life. If they need services, the services are brought into them. So we have about 65 residents at any one time at TigerPlace, which span this elderly population age. Almost everybody has at least one chronic illness, and there's a great number of them that have multiple chronic illnesses. And so part of the issue there at TigerPlace becomes one of how do you manage this instance of all these chronic conditions. There are some cognitive problems. There are certainly lots of physical problems. We try to keep the residents as socially active as possible, so there's lots of activities for them to do. So as we were working with our clinical partners, we eventually came to use this graph as kind of a motivation for what it was we wanted to accomplish with the technology. Our nursing partners have told us that if you look at a typical trajectory as a person ages, you'll see this sort of red stair-step fashion, where somebody will go along on a plateau for a time until something dramatic happens, and they drop down pretty dramatically to another level, lower level, until the next big thing happens and they drop down again. And our hypothesis was that if we could go in with, if we could first of all detect that decline, the very beginning of that decline, or even better yet, predict when that decline was likely to occur, that we would have a small window of opportunity at which an intervention could be offered, and we could then literally change that trajectory of functional decline to look to something closer like this dotted green line. Some people call this squaring the life curve. Well, so we looked at this as an engineering view. What we want to do is optimize the area under the curve, and in order to do that, we need feedback. And so this eventually came to develop this idea of monitoring systems in the home. So we want to assess some behavioral patterns using this in-home sensing, and this includes assessing gait and activity patterns, recognizing when those patterns change, so that we can use that then as a sign of early health decline. And then we now have an automated health alert system in place where we send out health alerts. This actually ends up being used as a clinical decision support system, and I'll show you how that works. So ultimately, if you can in fact square this life curve, it gives you a higher quality of life and also has the potential of saving a huge amount of money. So everybody benefits. So here's our goal: keeping older adults functionally active, even if it means playing polka music. This happens to be my mom and dad, by the way. My father just turned 91. My mother's 88. They really do play polka music. But they've lived together for over 65 years. And as a result, they know each other very well. And they know when one of them experiences health problems or experiences changes that might relate to health problems. And so this just happened recently with my mother, where my father noticed some problem and he convinced her to go in and see the doctor, and she was able to correct a very small problem before it became a huge problem. And she ended up spending one night in the hospital, but she came home early after that, so they were able to fix this problem. But of course, not everybody has the benefit of living with somebody for 65 plus years. And so we'd like to have the sensors in place to be able to do this effectively. We probably can't do it as well as my father can, but we can certainly do some things that will identify some changes. So I'm going to show you how these health alerts get used as a clinical decision support system. So here's the system that we have in place at TigerPlace. Now when we started this, we were using pretty simple sensors, passive infrared motion sensors, a bed sensor that is a little bit clunky but gives you some information. A chair sensor a bed sensor can be deployed on the chairs, recliner chairs for people that sometimes spend a lot of their evening or their nighttime in a recliner chair. We have a stove temperature sensor as well. We have an electronic health record that we've developed as well that includes some additional health assessments that are not generally included in this population. So we have a system that will process the sensor data and recognize when there are pattern changes, and it will generate an alert. The alerts are sent in the form of email to the clinical staff, and we rely on the clinicians then to interpret the clinical relevance of this alert, and they then do the nursing care coordination effort, and we also ask them to rate the clinical relevance of the alert, and those are used then as feedback into the system to give us ground truth on what constitutes a clinically relevant health alert. So here's some pictures of the sensors deployed in TigerPlace. As I said, we use very simple, off-the-shelf, passive infrared motion sensors. You can see here a picture of the pneumatic bed sensor that we've been using since 2005. It's a simple pneumatic strip that lies on top of the mattress, captures low, normal, and high pulse rate and respiration rate, and also gives you bed restlessness. This is a typical network in TigerPlace. TigerPlace has different apartment sizes. This is what a one-bedroom apartment looks like. Has about a dozen motion sensors, one bed sensor, stove temperature sensor, and then a computer that logs this. So we've been logging data in TigerPlace now since October of 2005 with an average installation time of about 2 years. If you really want to see the longevity and how this affects how the sensor data correlates to medical conditions, you really have to have them deployed over a fairly long period of time so you can begin to see those changes. We have one individual, in fact, who's had a sensor network installed in his home since November of 2005. So he's our star participant. We have lots and lots of data on him. And we've seen some interesting cases of him because we've seen him go through knee replacement surgery and the rehabilitation associated with that. We've seen him go through back surgery and the rehab for that. Now he just had knee replacement surgery on the other knee, and so we're going to see the rehab associated with that. So here's what an email alert looks like. Now, when we started this out, we couldn't find any other work in which this had been done or anybody specifically to tell us a ground truth on what constitutes a good clinically relevant health alert. And so we purposely cast this algorithm to be very wide and give us, it's a very simple algorithm, uses some very simple statistical parameters on each individual parameter, which actually correlates very nicely to the sensor events that are captured. And we wanted to make sure that we captured all of the events, or at least most of them, as much as possible, recognizing that there were going to be a lot of false alarms. And now, as I said, we're also having the clinicians give us a rating of whether or not these alerts are actually good from a clinical perspective. And we wanted to have a ground truth database that had some good clinically relevant alerts and some poor clinically relevant alerts so that we could then use that to go back and refine the algorithms. So this is a very simple algorithm that generates these alerts. You'll see that there's a link in here to a sensor interface. It's a web-based interface that makes it very easy for the clinicians to use. They simply click on that link and it pops up a window that gives them the sensor data and the context of what else is going on. And they can zoom in and zoom out and look at different parameters, and that helps them then assess whether or not that has some clinical relevance. And of course, the clinicians also have access to the electronic health record as well. So this is one of the displays that is in that interactive web interface. And this, in fact, is one that was related to a health alert. So the way this system is set up, each column represents one day. And you'll see the hours of the day range from midnight at the top to 11 p.m. at night. And each one of those red lines correlates to a bathroom visit. So in this type, you see that this particular individual did not have a pattern of using the bathroom in the early morning hours, between midnight and 7 a.m., and then suddenly developed this pattern of more bathroom visits. And in fact, there was a bathroom alert that was generated, and it turned out that this individual, in fact, had a urinary tract infection. So the clinicians were able to get the person assessed, identify that there really was a urinary tract infection, and be able to get this person the right kind of treatment so that that was addressed very quickly. So it turns out that something that might be seemingly as simple as a urinary tract infection can end up becoming quite complicated for elderly people. And it can present in very interesting ways if it's not treated very early, which can then complicate the ultimate diagnosis of it. So it can actually give people cognitive symptoms, for cognitive decline, dementia symptoms, if it progresses to a certain extent. So it's important to get these kinds of situations recognized early and treated early so that they can be resolved while the problem is really small. So that's an example of a case that was caught. So the second link that's shown in here then is the link that the clinicians click on to provide feedback, and they're asked to give a rating 1 through 5 of whether or not that's a good clinically relevant alert versus a poor clinically relevant alert. And as I said, we use that for future refinement of the algorithms. So, yes?
So the alert, this message says that there's increase in bed restlessness. When they click in on the left URL, they will see the same graph that you just shown us?
No, they see the one that has to do with that. I'm sorry, the one I showed you doesn't correlate to this alert. But no, they would see a different graph. But the one that I showed you here is one of the things that they can see in that sensor web-based interface.
Is it trying to direct them to the relevant graph to the specific alert, or is it they just now get access to the sensor data and they now try to dig what is the?
Yes, there is a kind of a default position that we give them that is based on the day that the alert was generated and the time period over which the alert was generated. So when we did this study initially, we had alerts being detected based on a 24-hour period, and then just looking at the nighttime hours and then looking at the daytime hours. And so the system is designed to pop up the appropriate time window, but then it relies on the clinicians to dig a little bit further and see what other features, what other parameters they want to look at. And as I said, you can zoom in and you can zoom out and look at different time periods if you want to see it in a larger context. The clinicians, so the web interface was developed iteratively with feedback from the clinicians, and a lot of the way we set this up was driven directly by what they said they wanted. So for instance, the default is a 2-week window because that's what they said they wanted. Yeah?
In that example, why did it take 4 days for the alert to fire?
Well, the way the algorithm is set up, it uses both the mean of the previous 14 days as well as the standard deviation. And there was actually, if you go farther back in this particular individual, there were 1 or 2 nighttime bathroom visits. And so that's just the way that this parameter happens to be set up. As I said, it's a very simple algorithm. Okay, so we did this study as a prospective study for 1 year. This was funded by the NIH. And we actually ran it as a test with an intervention group in which there was a set of people. This was a relatively small group of people. It was about 20 people in each group. But it was run as a controlled experiment where we had people receiving the health alerts and then a control group that were not getting any health alerts. And we were able to show that we had, in fact, statistically significant differences in the health outcomes between this control group and the intervention group. Now, I said here that they showed up after a year. And in fact, some of these differences showed up after 6 months, which I found was particularly stunning. I might also point out that the residents at TigerPlace, because of the fact of the way this nursing care coordination is delivered, all of the residents at TigerPlace get really, really good care, probably better than they would get anywhere else. And so it was stunning to me to see that we could add this really simple algorithm with relatively simple sensors, and that we could still see a statistically significant difference in the health outcomes between this control group that's already getting really, really good care versus the ones that we just added this other little piece on top of with the technology. So it showed up in this case on the gait parameters and also in the grip strength. This is some of the experiments that we did for actually doing the measurements to assess the clinical outcomes. But one thing, yes?
I'm curious, do the staff and the patients, the residents, know who's in the control group in the intervention?
Yes, they do, yeah. I don't think that that affects the treatment though, but yes, they do know.
So the staff is the same staff that's treating both groups, right?
Yes.
The medical staff is the same and nursing staff is the same.
Yes, that's right.
The only difference whether they get this automatic alerts or not.
Yes, that's correct. Yeah, and in fact, at the end of this one-year study, it was the nurses that said, we believe in this so much that we want to put this in place for all of the TigerPlace residents that have sensor networks installed. Now, as a matter of a practical thing, we only run about 25 or so sensor networks at any one time because we're doing this, on a university research group. So the logistics of that is about what we can manage. But we could, in fact, do it with everybody, and the clinicians would be happy with that. They really like the clinical alerts. But what we found is that, in fact, because we had cast this very wide net, that about half of those health alerts were false alarms. Now, in part, that's because we started out, over time, we were tweaking the algorithm a little bit. And when we started out, we really had a lot of false alarms, and we were able to reduce that a little bit. But overall, about half of them were false alarms. But nonetheless, we were able then to use that database that we collected to refine the alert algorithms and see what we could do. So one of the things that we wanted to look at, sort of an obvious thing, is instead of looking at a single parameter one by one, what happened if we looked at a multidimensional feature vector? And so this is one of the things we started to look at. And in fact, I'm going to show you here a couple of examples that was done by one of my master's students, where we wanted to look at the difference between doing domain knowledge only versus something that involved training data. And so we looked at a fuzzy pattern tree, which did not involve any training, and then an SVM that does use training data. And in the end, after looking at this, doing some feature selection and so forth, we ended up using these 6 features, which turn out to be quite significant. And in fact, a lot of them have to do with nighttime activity. This turns out to be a very promising way of looking at this as well. So here's what that 6-dimensional feature space looks like as a PCA reduction. Now this was another hypothesis that we had, was that these normal days, the non-alert days, would sort of form a cluster in this feature space, and that the abnormal days, the ones that would justify an alert, would in fact be outliers to this cluster. And that's kind of what that looks like, although you can see it's not completely that way. There's some red normal days that are kind of a little bit outside. But that's kind of what we've got. So we set up this fuzzy pattern tree to look like this, except that the OR operators here were using a Jaeger operator such that if you had a little bit of a change here and a little bit of a change here and a little bit of change here, that it created a cumulative effect that would generate an alert. So it's not just an OR the way it's listed here. And then we also did an SVM, and here's the results that we got. Interestingly, almost exactly the same results between this domain knowledge only, no training involved, system versus the SVM. Was there a question?
Yeah, it was a question about the slide on the points, how they look in the PCA space. Is this how do you select the normal days? I assume there are a lot more normal days than.
Well, so this is based on the feedback that we got from the clinicians in the ratings. So what I'm showing you here, out of all these health alerts that were generated, some of them the nurses said were not clinically relevant, and so those are the ones that show up as the normal days.
I see. So these are actually the false positive days versus the true positive days for across individuals?
Yes.
Okay.
So these are all things that the original algorithm would have fired on, and then you have.
Yes, that's right. Yes, that's right. Yeah. So as I said, about half of them originally were false alarms. So we got up to a classification rate here of about 85%. I think this is still a very simplistic look at this, and there's a lot more that we can do. Oops, did something just fall off? Oh, sorry. I thought I lost my microphone. So I think there's a lot more that can be done here. This was sort of a first stab to show that in fact this makes sense. And we have some other things that we're working on next to be able to refine this further. Let me show you another picture here, which is taken from one of the retrospective analysis using the bed sensor data. So I mentioned that this bed sensor produces these low, normal, and high pulse and respiration rates. And this is an example of an individual that had an ER visit at the end here that's shown, and then a hospitalization. And in fact, this is a 96-year-old woman that ended up dying very soon after she went into the hospital. But you can see the changes in the sensor data patterns leading up to that hospitalization, ER visit. We went back retrospectively and ran the alert algorithm, and what we saw is that we actually would have generated an alert 40 days before that emergency room visit. So, who knows whether we could have done anything to have changed the ultimate outcome, but in fact, we would have generated an alert 40 days before that ER visit. So it shows the potential for capturing this kind of physiological data and particular bed sensor data. So what I'm going to show you next then is our take on a different bed sensor, something that captures, in fact, quantitative sensing, quantitative pulse and respiration. So this is built by one of our grad students who went to a hardware store, came back with $20 worth of supplies, and put together this hydraulic bed sensor, which is basically a tube of water. It actually works better if you put it underneath the mattress, which is nice. It's very non-invasive. And this is a kind of signal that you get from this hydraulic bed transducer. So it captures the superposition of the respiration and the ballisticardiogram. So you may be familiar with the electrocardiogram. The ballisticardiogram is the mechanical effect of the electrical pulse of the heartbeat. So it's literally the mechanical effect of the blood flow as it's pulsing through your body. And it kind of mirrors that electrocardiogram signal. And we've got several different algorithms for processing out the pulse data. I'm going to show you one of them in particular here. We've done a little bit of modifications to it. We've now come up with this design that's actually a 4-transducer design that's located like this across the bed. So the sensor, in fact, hits you. And the idea is that it would hit you about your upper torso area. And there's 4 of them so that as you roll around at night, it increases your chances of being on one. But in fact, you actually can sometimes get really good signals out of all of them. So here's an example that's taken from one study where you can see the filtered reading. Now we've now filtered out the respiration so that you're seeing just the ballisticardiogram effect. And you can see the ballisticardiogram, the characteristic ballisticardiogram signal that you get from this. So this is what the ballisticardiogram looks like. And they actually call this as a IJKL. So it's labeled somewhat similar or analogous to the electrocardiogram. But this main peak is called the J peak. And so this particular algorithm then is designed to try to identify the J peak of that signal after the respiration has been filtered out. And we extract some features from each of the peak. You can see the features that are run there. We then run a clustering algorithm on it, looking for 2 clusters. The idea is that the smaller cluster would contain the J peak, and the larger cluster would contain the rest of the peaks. And you see there's several small peaks involved in there, but there's only, ideally, only one large peak. Whoops. And here's an example of some heartbeats detected using that algorithm. The ground truth is captured using a finger sensor, so you can see what that looks like. And then the little circles up on top show the J peak that has been detected using that algorithm. There's other ways of processing this, of course. We have one algorithm that operates in the frequency domain and just captures the actual pulse rate. But the nice thing about this is that by identifying each individual peak or each individual heartbeat, you also get this beat-to-beat interval, and you can see what the distribution looks like. And you can see here what you get as a beat-to-beat interval basis on the hydraulic bed sensor versus the ground truth system. And so we're in the process of now of incorporating that hydraulic bed sensor into our health alert system so that that can become this additional, more finely grained data to capture for health data. In fact, we've just finished installing 15 systems in Cedar Falls, Iowa, in a 100-year-old building, which is assisted living. And we're in the process of finalizing a design of an embedded system for this hydraulic bed sensor, but that's going to be installed there as well. So let me give you a couple of case studies from TigerPlace. I have a colleague who is very interested in seeing how this can be applied to cognitive problems and other mental health problems such as depression. And so I'm going to show you a couple of instances of that. And it uses what we call this motion density map. And this is set up as that previous bathroom visit map is set up, where each column represents one day, and then you have the vertical axis going from midnight to 11 p.m. And here the color shows the density of the motion sensor readings. So the motion sensors that we use will generate an event about every 7 seconds if there's continuous motion in the room, in the area of detection. And that can be used as an artifact to determine a sedentary kind of pattern versus a more active, what we might call puttering kind of style. And so you actually get a measure then by processing it as a density, number of events per unit time, you get a measure of how sedentary or active a particular individual is. That's based on the color. The black here indicates the time away from home, which is also captured. And so for a healthy individual, you'd like to see virtually no activity at night, which indicates that they're sleeping really well. And then a healthy individual usually will have a pretty consistent time while they wake up and a consistent time that they go to bed. Here you see the black regions that coincide to eating in the common dining area, so breakfast. This individual does his own lunches. This corresponds to the evening meal. And then TigerPlace has a movie theater. And so the evening hours are probably when this individual goes out and watches a movie in the movie theater. So here's a couple of examples then of capturing this kind of data for depression and dementia. So this particular individual had depression and dementia, both. You can see what this pattern looks like in July. And then as this exacerbation of these mental health conditions occurred, the individual withdrew. And you can see what's really particularly stunning here is basically stopped leaving the apartment. But the individual was ultimately treated and then sort of returned back to what was a more normal case for that individual. Here's another example that also is depression. Again, you can see, although this person had depression, it was managed by a geriatric psychiatrist. Then there was some additional personal losses for this particular person, and this person stopped eating, stopped going out. You can see a pretty dramatic change, and then ultimately after intervention was able to get back to a more normal life pattern. We also have a computational algorithm for capturing the actual pattern changes. So there's some individual features that you can capture from this, but we also process it using image texture features to try and capture the overall pattern of this as well, and that is also then can be used to determine health changes. So let me also then jump to an area that you might all appreciate, because this one uses the Kinect. We have now in 10 apartments at TigerPlace, we have Gait Analysis systems. We have a couple of grants that are running concurrently that are looking at vision data, acoustic data, radar data. When the Kinect became available, we all jumped on that, went out. I mean, everybody, of course, in academia went out, bought a bunch of Kinects and started using them. So this is being used now in 10 apartments for extracting gait analysis information. And although it's not yet tied into the health alert system, I'm going to show you the kind of gait data that we can capture from it. Now, we're doing this in this main living area for the people at TigerPlace. And as a result of that, we have a fairly large area that we're trying to cover. Some of these apartments span 25, 30 feet across. And so we're not using the SDK, and we're not capturing the skeletal model. We're just processing data on the depth imagery directly. You can see some examples of the segmented person that's been pulled out of here as the foreground, and then we project that into a 3D space to make a 3D model of a person as they walk around. And we're capturing the gait parameters directly from that. So this is a picture of a Kinect installed in one of the TigerPlace apartments. We have it installed up close to the ceiling over the front door. We did some testing in the lab to show that we got a little bit better results if we had the person walking towards and away from the Kinect as opposed to walking laterally. And so we set this up to try and optimize our walk so that they would be mostly towards, we'd have a long span towards and away from the Kinect. We've set this up in TigerPlace so that the cabinets above the refrigerator are all outfitted with network ports and power, and so that's where we put the computer. And then we have a nice little conduit that goes around here that hides the cable so that it looks pretty discreet. People in TigerPlace are kind of particular about how their apartments look, and we found that if you want to put this in their home, it has to look nice. Otherwise, they're not willing to do this. And in fact, the study here calls for these systems to be in place for 2 years. So we can imagine if somebody came to you and said, I wanted to install something in your home for 2 years, you'd want it to look nice too, right? So here's a depiction of how the gait parameters are estimated. For the Kinect system, we use the lower part of the body, the legs, and we're looking at capturing these walks whenever possible so that you can see here this correlation coefficient that is captured as a person walks. So one side of this, like the peak here, corresponds to the left step, and this corresponds to the right step. And I'll direct you to this paper here if you want to look at some more details. Because these are running in the home, and it's a very unstructured environment, we have to do some kind of a segmentation on the actual walks. And so we pull out of all of this data of somebody walking around, we pull out individual walk sequences based on the straightness of the walk, some minimal walking speed, as well as the number of steps, so that we can actually get what are useful stride information. So we get from each walk a time stamp, the centroid of the person, of this segmented person, and then if we can possibly get the stride data, we'll get that as well. But you'll see here what happens is because of occlusions, we can't always get the individual stride data. These apartments are very cluttered. You know, people have lots of stuff that they want to keep in their home, and they're not going to just push it aside, right? If you install something in their home, you have to fit your thing into their particular configuration. So in some cases, we can get all 4 parameters where we can actually get the stride time as well as the stride length. In some cases, we cannot. And so we've figured out how to deal with that on the cases that we can't get all 4 parameters. So in order to extract trends of people, remember we're looking for changes in these patterns over time, we take a 2-step process here where we first try and estimate a model of a particular person's gait pattern, which represents here actually the height, the walking speed, the stride time, and the stride length. And so we do this model estimation by fitting a Gaussian mixture model with the number of residents over this 4D data that we capture. So what's shown here is a depiction. This of course only shows 2 dimensions, the walking speed and the height, for a resident that has a couple that lives there. And you see what happens is that you typically would get, for a 2-resident environment, you would get 2 clusters, 1 for each resident. In fact, this particular couple has grandchildren that come over and visit a lot. And you can see all these short people are grandchildren. And you get a bunch of outliers as well that represent other walks. But what we're really trying to do is capture what turns out to be the center of these clusters, 1 for each of the residents. And then that also does a nice job of being able to deal with the multi-resident environment. So we then try to capture these trends of these models over time. I think I'm going to point you to this paper, and we're going to gloss over some of this because I see we're kind of running low on time. Let me show you some examples. This is a single resident apartment. Again, you have lots of visitors that are shown here as the outliers, but you can see kind of a depiction of the gait pattern that's been modeled here. And you can see in here that these small black dots are the walks that don't have any stride data, whereas the blue and green dots are the ones that have the stride data. But you can kind of see how this mode finding algorithm works. Here's an example of that 2-resident apartment. Again, this makes it a little bit easier because the wife happens to be much shorter than the husband. That isn't always the case, but if you look at this in 4-dimensional space, it increases your possibility of being able to separate out these multiple clusters. So this is data that was acquired over a 7-month period, and you can see there were lots of walks that were captured during this time period. So to estimate the trends, we use a sliding window with a step size of 1 day, and we compute the contribution of each walk by looking at the likelihood that it was from the resident. We also reduce the short walk, the impact of the short walks, as you can see here. And you end up with something that looks like this. So this is the trends for about 6 months of that one case, that first one that I showed you. Now you can do this over a different number of days. You can see the kind of noise that you get if you do it over a 2-day window versus a 14-day window. This is a particularly interesting case because this is an instance where this resident was in the hospital due to surgery, required surgery, came back then at the end of October, and you can see where this is picking this up now, the first part of November, was doing intensive physical therapy, and as a result, this gait pattern was changing. And you can see what's happening here. The stride time is going down, which is good. The speed is going up, which is also good. As this person was getting better and rehabilitating, was showing an increasing pattern. That's better than the other way around. So this shows the second case with the 2 residents, and I did this just for the 14-day window. So in fact, this first one is the husband, and this is the wife. The husband here, in fact, was eventually diagnosed with cognitive problems. And what you see here is a decreasing speed and a decreasing stride length. So taking shorter steps, which is consistent with somebody who is beginning to have cognitive problems. So this is something that's kind of interesting, that in fact looking at gait changes will capture not only physical problems but also cognitive problems. And that's exactly what we're seeing here. The wife, in fact, has Parkinson's, and interestingly enough, over this time period, you do not see much of a change. She was undergoing some treatment, and apparently it was pretty effective during that time period. So, yes, do you have a question about this?
On the first resident, there is on the right side toward the end of the period, it seems as if there is some bump. Do you know what this corresponds to?
I don't know what that corresponds to. You're right, this does seem like this is a little bit of a bump here. And I'd have to take a closer look to see it's possible that he was getting some sort of therapy. I don't know. Okay, well, so let me just go to the last area here that I wanted to cover. We've also been very interested in doing fall detection because, of course, being able to detect falls very early and get people treatment very early, get them help or get them up off of the floor and so forth early, also speaks to being able to minimize the health risks and damages. So we've been looking at a number of different non-wearable detection modes, acoustic, PIR, radar, vision, also the Kinect. What I'm going to show you here is some work that we've been doing with acoustic arrays. One of the problems that you have when you try to do fall detection for elderly people is, you don't want the elderly people to fall. We certainly don't want to ask them to fall. And so we bring in stunt actors, and we have the stunt actors fall, but we also want to detect them, we want to capture what would be realistic falls. And so we have a whole protocol set up where we actually train stunt actors on how to fall like elderly people. And there's 21 different types of falls. This, in fact, is my colleague, Marilyn Rance, who is training Adrienne how to fall off of a chair so that she looks like an elderly person fall. We give the stunt actors mats, though. Actually, they don't need them, but we feel like we need to give them mats. So this is an example of an acoustic array system that we've been looking at. It's a circular array of 8 microphones. You can see it's obviously designed by a grad student. Nonetheless, it works, even though it seems to be somewhat aesthetically challenged. So the idea behind this circular array is that we want to detect the location of the sound because, one justification for doing that is to use beamforming to improve the acoustic processing. But the other reason for it is to be able to detect whether or not the sound source came from the ground level or whether it came from above the ground level. So if the source is from the ground level, it increases your chances of that being from a fall as opposed to being above the ground level. And in addition to that, there is a acoustic signature of a person falling down compared to an inanimate object falling down. So again, we have stunt actors that come in and do these falls. Initially, these were done in the lab, and so this is a list of all the different falls you can see that are part of our suite of falls, some from a standing position, some from a sitting position, some from a lying down position. And then there's a bunch of different non-fall activities that we did to have the other class, and in this case involved making a lot of noises that we could then look at, compare against a real fall. So we also wanted to add noise into the environment to try and get to something that looked a little bit more realistic. So I'm going to show you two cases here where we looked at adding background white noise only, and then another case where we added this white noise as well as a TV interference. And we did this using, first of all, a single microphone without any kind of beamforming or height taken into account. We also did it using beamforming, and then we did it with the beamforming and the source height to be able to prune out these extra problems. So here's what the ROC curve looks like. And of course, if you look at this with the so-called clean rate here, you get very good results. This is in the lab, of course. But you can see that, in fact, the best result here is the beamforming with the height. In fact, nearly perfect results. When you add in the TV interference, it's not quite as good, although it still is pretty good. There's always the question of how good is good enough if you're really going to deploy this in a home setting. And then there's another example here where we actually had stunt actors going into the TigerPlace apartments, and we had set up the acoustic array system in there, and you can see what that system looks like. In fact, interestingly enough, we had trained this system with falls that were performed in the lab on the mattress, and then tested them using the stunt actor data in TigerPlace, and got reasonably good results out of that. So here's our, yes?
Was the overall mandate not to have the person under test wear anything?
Oh, so why did we constrain ourselves to non-wearable systems as opposed to wearable?
I realize it's about as minimally invasive as you can get. So did you mandate that they would not have to wear anything?
Yeah, so this is an interesting question. We were having this discussion earlier today. When I first got involved with this, because of the fact that this came from our clinical partners, it was really the nurses that said, let's not put sensors on people. They were quite adamant about that. They really didn't think that the population, our target population, would be interested in wearing stuff. The problem is that this kind of bears out with other work that we've done, is that they're happy to comply as long as they're feeling well, and as soon as they're not feeling well, then they don't want to be bothered. One of my clinical partners happens to be a family medicine MD, put it this way. She said, when somebody gets to be 80-something, they do what they want, and when they get to be 90-something, they do it with an attitude. They're going to do what they want, and you can't coerce them. So we just decided we were going to see how far we could get with totally non-wearable systems. And certainly, a lot of people end up experiencing falls when they get up in the middle of the night to use the bathroom, and they're unlikely to have something on, some wearable system on during that time period. So we wanted to see how far we could get with totally non-wearable systems.
Let me just add, I definitely agree with Mary in that, but there was a talk recently that I mentioned to you. This company, they developed something which looks like a Band-Aid, which has all the electronics and all the power, and you can put it on for about a week. So you just stick it somewhere on your body and put it on for a week. And this sounds like something that might work because you don't have to put it on and off when you go to sleep. But even if it's something like a watch, you can't imagine someone wearing it 24/7.
Yeah, so I guess to answer your question, it was sort of a mandate to us by our clinical partners to look at totally non-wearable systems, and so that's what we focused on. I get some grief about that from time to time from other people. At any rate, this shows some of the individuals that have been involved with this research over the years, and I've tried to highlight the ones that have particularly contributed to this work. So if you want to go back and try and pick out their papers, Eric Stone is the one who's been involved with the Kinect work. Dane Guevara is the one who did the early illness alerts. Lisette and David worked on the bed sensor. Shuang worked on the motion density maps, and Yun Lee is the one who's worked on the acoustic system. But it's quite a multidisciplinary group of people. We certainly couldn't do this work without our clinical partners, and they've kept us honest in terms of being able to do something that that certainly respects our target population, as well as something that would be useful for them. And so we've tried to make this really driven by the actual problems and challenges that this target population has. So I'd like to acknowledge our funding agencies. Much of this work has been funded by the National Science Foundation, NIH, and ROC. And there's the website. If you're interested in picking out some of the papers, most of them are online, or they're at places that, like IEEE Explore, where you can readily get them. So thank you very much. Here's our mission. I'll end with Mom and Dad. They also garden. So thank you very much. So are there other questions?
Have you thought about remote temperature sensing?
Yeah, so we were talking about that this morning. We've not looked at that, but I can see where that might be useful. And what would you suggest as technology, sensing technology, for being able to capture that?
Randy and I have talked about this, and one of the options might be an IR camera, let's say above the bed, where your head tends to be in a certain area, and then during the night it would record your body temperature at a time when you're not active.
Yeah, and actually I might note that the way our bed sensor works in capturing pulse and respiration, it's very difficult to capture that while a person is moving around. So because the restlessness ends up showing up as a very high amplitude noise. And so in fact, we also capture pulse and respiration basically when a person's still. But I can see where temperature would be useful. Did you have another question related to that?
Yeah, so some patients I assume are diabetic and might be doing glucose tests during the day and things like that. Do you take any of this extra information that you might have on some patients and try to add it to the database?
Well, so this would be an obvious thing to do, would be to add in data coming from the electronic health record. We have not yet gotten to that point. I do have a colleague of mine who is now looking at this problem like a data mining problem, and so he's literally looking at the electronic health record data, which is really the medical record data that the nurses have access to, as well as our sensor data, and looking for correlations that way. And certainly you could, if you had medical records, you could incorporate that into this general health alert system, or you could use that as a context. We've not gone there yet, but you're right, that's the next obvious thing to do. There's another question? Yeah.
In your clinical study, did you measure the effect of being in the treatment or control group on the amount of attention that the individuals receive from the nursing and medical staff?
You mean, did the control group or did the intervention group just get more attention in terms of time compared to the control group?
Something like that, or the other way around. I don't know, maybe it could go either way. I'm just curious whether or not you have measures on that.
I don't know that we actually captured it in those terms, like the amount of time that they spent with each individuals. You know, one might expect that they would maybe spend more time with the intervention group because of the fact that they're getting these alerts, and if something looks suspicious, then they need to go take a closer look with this individual, which would maybe necessitate them spending more time with that individual. I don't think that parameter was ever pulled out, though, that I recall. Yes?
Yeah, I have a question. So in the over the years, you've assembled a lot of interesting data that the machine learning community would probably like to play with. But it is patient data, so there could be some privacy issues. So how easy or difficult is it for you to share the database that you've assembled?
Yes, I get this question all the time. Of course, it would certainly push this work forward if we, in fact, could distribute it to the machine learning community. I'm reluctant to do that because so far we're doing this in relatively small numbers, and up until very recently it's all been done at TigerPlace at one facility. And so it would not be difficult, even without actual identifying data, like names and so forth, it wouldn't be difficult to make those correlations, and so I'm reluctant to distribute it. We had talked about being able to distribute it. In fact, I actually have a proposal in review that would allow us to do that, because we would do some processing to the data, change the dates, and try and scramble some things so that it becomes harder to try and identify it. The other thing that we can do now that we've got this database on the clinically relevant alerts, instead of distributing actual medical record data, we can distribute sort of in a binary fashion. Does that alert constitute a clinically relevant alert versus not a clinically relevant alert? In fact, it's a scale from 1 to 5. So you could get some measure of the significance of it from a health perspective without really releasing actual health data. So that's what my plan is to do. If that proposal gets funded, we'll have the ability to put that in a form that we hope will be at least harder to identify. And at least I would feel more comfortable releasing that than in its current form. But yes, we have lots of data. I'm running out of server space. So then at this facility in Cedar Falls, we've got motion sensors, we've got Kinects, and now we're going to have the bed sensor as well. So we are just collecting a ridiculous amount of data.
Next speaker again.
Okay.